When we work with matrix equations, soon in our applications we'll apply these different ideas of inverses. After all, we already know how to solve systems of equations, and it really never required using inverses. We could do it using Gaussian elimination. And in fact, if the solution isn't unique, inverses aren't going to do us any good anyway. But there are situations where we have equations involving matrices and inverses, and we want to solve that equation symbolically. So the best way to do that is by utilizing properties of inverses. So the first property here, and what we're going to do in this video is just provide some of the logic, the reasoning for why these statements are true. So if A is an invertible matrix, so notice here that we are making the assumption that the matrix we're dealing with is invertible. If it's not, then this property will not apply. Then A inverse is invertible, and A inverse inverse equals A. Okay, so that just sort of means that the inverse of the inverse is A. Well, let's go ahead and see if we can show that. So we want to take A inverse, and we want to multiply it by something, which for now maybe we'll just call matrix X, such that I get the identity matrix. So what we do know from this statement is that X is the inverse of A inverse. So just think of A inverse as just some matrix. That's just some matrix right there. And this statement right here is just saying that that matrix has an inverse. Okay, well, if it does, then it would have to be the case that the only matrix that I know of that when I multiply it by A inverse that I'm going to get I is, in this case, I would have to be able to conclude that X is equal to A. Okay, so that means that the inverse of A inverse would be A. Now also I could write that the other way around. I could say that it has to be the case that X times A inverse is equal to I. And again, we're just going to think briefly about this as just some matrix, and really this is just the inverse of that some matrix. So what would that matrix be? Well, I already know that if I take A times A inverse, I get I, and therefore I should be able to conclude with pretty relative ease that X is equal to A. All right, and so in either case we see that X is equal to A, and therefore the inverse of the inverse matrix has to be A. Okay, now that might not seem like something you would normally need to prove, but we are arguing that you can kind of keep inverting back and forth between these two matrices, A and its inverse. So if you invert A, you get A inverse. If you invert A inverse, you get back to A. Property B is an interesting one. It's one that we've seen before, but with transposes. If A and B are n by n invertible matrices, then so is AB. And the inverse of AB is the product of the inverses of A and B in the reverse order. Okay, so this was the same thing with transposes. If you recall, if we took the product of two matrices and then transposed it, we could multiply B transpose A transpose instead. Before, we kind of made a dimensional argument about A and B, and then if you transpose them and multiply them in reverse, you get the same dimensions. In this case, they're both square matrices, so we can't really make a dimensional argument to help us establish our point. But what we want to show is that the inverse of AB is equal to B inverse times A inverse. Well, let's start with A times B. So we know AB. Again, think about AB as just one matrix instead of two separate matrices. Okay, so AB, I want to multiply it by something to get the identity. Well, if AB is invertible, then that means that that quantity has an inverse matrix such that I will get I. Well, another way I could think about this is to take AB, and to get the identity matrix, I could take B and multiply it by B inverse. So what that would give me right there is that would cancel out and give me the identity matrix. And then what I would be left with is AI, and A times I is just going to be the A matrix, since the identity matrix will not change the A matrix in any way. So if I then take A and I multiply it by A inverse, so keep in mind that this whole product right here has resulted in A, and if I then multiply that by A inverse, I get the identity matrix. And so since it is the case that AB times B inverse A inverse gives me I, that must mean that this right here is the inverse of AB. Because any matrix that multiplies another matrix and produces the identity is considered to be the inverse matrix by definition. We could do the same thing the other way around. We could say, well, what times AB gives me I? And in that case, we would find that B inverse times A inverse times AB, again, this will cancel out to give me the identity, leaving me with just B inverse times B, which gives me the identity. And so since that multiplication again produces the identity, again, I could conclude that the inverse of this guy must be this guy. And another way to write that is AB quantity inverse. So those are very useful properties that we like to use quite often. Now, you don't need to prove these every time. The goal is just to have some intuition behind why they're true. This one says that the inverse of A transpose is the same thing as the inverse of A and then transposed. Let's see if we can make some sense of this. So again, we're going to make kind of this funky looking argument. And we can go ahead and write that we want to find the inverse of A transpose, right? So we want to say, what is the inverse of A transpose? Well, once again, if I take A transpose and I multiply it by some matrix, that should give me the identity. Now, let me just choose briefly. We know that what this is going to be right here, that is the inverse of A transpose. So that's how I want you to think about that. X is the inverse of A transpose. And I'm wondering, is there any other way to write it other than the inverse of A transpose? Well, let me make this argument. Let's suppose that it were true that the inverse of A transpose was the inverse of A transposed. Okay, now notice these are different. This one is saying that X is the inverse of this matrix right here. Here I'm just saying, okay, what if I took A transpose and multiplied it by the inverse of A transposed? Well, by property of transposes, recall that if I multiply two matrices together and I transpose them, that's the same thing as B transpose A transpose. Well, working that in reverse, if what I have is B transpose A transpose, and since these two sides are equal, what I could do is reverse their order and put the transpose back at the top. Well, that's the same thing I could do here. I could say that A transpose times A inverse transpose is the second matrix times the first matrix transpose. And that's just me working from left to right of this equality. Now, my matrices are called something different, so don't let that distract you. A inverse is just a matrix. You can call it B if you want, and then later on plug A inverse back in. Now, wait a minute. Here I see that I have A inverse multiplied by A because of that equality that I could write, and I already know that that's the identity matrix. So what this gives me is the transpose of the identity matrix. And if you take the transpose of the identity, regardless of what size, let's say a 3 by 3, just so we have a little bit of intuition, the first column becomes the first row. And look at that, same row. The second column becomes the second row, if I transpose this. And the third column becomes the third row. And so we see that the transpose of the identity is just the identity, And so what we've just proven here is that the inverse of A transpose, which we wrote here in pink like this, can also be calculated by taking the inverse of A and then transposing that matrix. So these properties are just kind of used to simplify processes so that you can really take maybe a series of complex computations and reduce it to a smaller computation. You can appreciate this if you're working with massive matrices in a computer system, and if you could reduce the number of multiplications to maybe just 2 instead of 10 by using these different properties and maybe canceling things out, you could save a whole lot of computing power.